y'all feeling?
Pretty good.
Yeah. Glad to hear it. Anyone need anything or have any questions before we get started?
What you think about the eclipse?
It was fun. I had a good time watching. Felt particularly special because that was my birthday.
Ooh. Happy birthday.
Thank you. Yeah, it was nice. I watched it with my wife and made sure all the people that wanted to see it had glasses, and just had a really nice day. And we should have another one in about 5 to 7 years, statistically speaking. Actually, I guess speaking of eclipses, there are groups collecting the eclipse glasses to donate them to other schools and other parts of the world that will be having eclipses at other times this year. For example, there's only one in South America in August, and people are collecting glasses to send down there. So if you still have yours and you don't care to hang on to them, if you return them basically, I'll make sure that they get sent to people who will use them later this year. Any other questions or things on your mind before we get started? All right. Today, we are going to cover the last new thing that would be on the test before we take it. As a reminder, scheduling stuff. Test 2 will take place next week. I plan to spend Friday and lecture next week making sure to go over review stuff so that everyone is prepared for it, talk about all the things that will be on it, and look at all the practice questions and things that I'm going to post to Brightspace in the coming days. So this will be the last new material that will be on it, last couple of details about some wave specifics that I wanted to make sure to cover. Now, between now and the exam, the last thing we do, there is one or two more things I want to cover. We have a lab about electricity. I'm going to talk about the things about electricity I think everyone should know. And I might talk about light, depending on how much time we have during the semester. Anything along those lines that gets discussed between now and the last day of class, I'll make sure it won't be on test 2. So light and electricity, however much we cover of that, won't be on test 2. I'll make sure that there's a finite list of everything that will be on test 2, and then separately a finite list of everything that will be on the exam. So anything we cover between today and the exam will be on the exam, but not on test 2. And there will be lists of all those things. I feel like I'm repeating myself. Is that all clear? Okay. So, sound. We've been talking about waves. Sound is just a very specific type of wave. It exhibits all the same wave behaviors that we've been discussing up till now. We mentioned that all waves are traveling vibrations, and therefore all waves are just traveling energy. The wave itself is traveling energy. There's a couple different forms that traveling energy can take, different types of waves. And all different types of waves are kind of categorized 2 different ways. First way to categorize waves is by their shape, because there's kind of 2 different axes, 2 different modes that a wave can vibrate while it travels. All waves are traveling energy, and since they're traveling, that does mean they have to go somewhere. They have a velocity vector. So in this case, I'm just going to represent that as a straight line to the right. All waves have a velocity vector, and that has to point somewhere. And the 2 different wave shapes are classified based on what axis the wave is vibrating in relationship to its velocity vector. The 2 main wave shapes are transverse. This is arguably the one that most people tend to think of first when it comes to waves. This is like how we tend to visualize waves as humans. Transverse waves vibrate perpendicularly to the direction of travel. Their oscillation has to be in a different perpendicular axis to the axis of their velocity vector. So if this is the velocity vector for a transverse wave, the vibration has to be perpendicular to that. And so if it's moving rightward, the two axes that would be perpendicular to that are either up and down or in and out. Those both are axes perpendicular to this rightward pointing vector. And so a transverse wave might look something like that. The vibration is taking place up and down, and the vertical axis is perpendicular to the rightward axis. Technically, it could also be an in and out vibration, but it's kind of hard to draw that on a flat board. To try to show that in action, can I get someone to hold the other end of this again?
I can.
Thank you. Okay. So, the wave is going to have to travel along the length of the slinky. Transverse would look like this. So, the wave velocity is the axis of the slinky. Transverse would have it shaking either this way perpendicularly to that axis, or possibly even this way perpendicularly to that axis. Oh, I'm so sorry.
You're fine.
So this or this. As long as it's not the same axis as the travel, that is called transverse. And that is different still to longitudinal. This is perpendicular to the axis of travel, but it's technically possible to shake in the same axis as travel, which would look like this. Just kind of a pulse back and forth in the same axis. It's a little hard to see. Humans don't tend to visualize waves like this. But it is a different type of oscillation. Thank you very much. Sorry to knock your way. Sorry again. So if transverse waves oscillate perpendicularly to travel, longitudinal waves oscillate parallel to travel. If a longitudinal wave is traveling left to right, it is going to oscillate in the same axis as travel, which again looks kind of weird and is kind of hard to draw. Most visualizations of longitudinal waves will use something like a spring to physically represent it. And in this case, the wave pattern is going to be represented by bunched up coils versus spaced out coils. The wave exists here in the bunched up sections as opposed to the spaced out sections. So the bunched up coils are meant to represent where there is a wave, where there is energy traveling, and the bunched up, the spaced out sections are normal. But it is still traveling and oscillating in the same axis is the main difference. These are the two primary, all waves are traveling vibrations, and the vibration will either take place in the same axis as travel, if it's longitudinal, or in a perpendicular axis as travel if it is transverse. All waves fall into one of these two shapes, because all waves have to vibrate, and that vibration has to be either same axis or perpendicular axis. Sound all right so far? All right. Now, this is not the only binary categorization system for waves. There is technically a separate categorization system, which I would call wave form, or probably wave structure. Because in addition to the way that a wave is vibrating, we also sort waves based on what they are physically made of. And there are two main categories in this department. Mechanical waves require a physical medium in order for the wave to exist and to travel. And this is going to be most waves that you think of. If there is something physically shaking that the wave is physically traveling through, that is some type of mechanical wave. This includes ocean waves, which physically mechanically travel through water, earthquakes, which physically mechanically travel through earth, and sound, which physically mechanically travels through air. If it requires a physical medium, we call that a mechanical wave, because something is mechanically shaking. This is distinct from waves that don't require a physical medium to travel through, of which there's really only one major type: electromagnetic waves. This includes things like light and all of its different cousins. Light doesn't require a physical medium, and that's why it can travel through space where there is no medium, there is no air in space, and that's why you cannot hear in space. But you can still see in space because light doesn't need a medium. Light exists on its own. We call these electromagnetic waves because rather than being physically made up of some physical substance that is shaking, electromagnetic waves are physically made out of electromagnetism, and therefore they don't need anything physical to exist. They are basically just pure traveling energy in the form of an E field and an M field vibrating in tandem. They're very weird, and there's entire disciplines of science dedicated to just studying this. But those are the two major classification systems for waves. There's either direction of vibration, perpendicular for transverse, parallel for longitudinal, or wave structure, mechanical for requiring a medium, and electromagnetic for not requiring a medium. All waves can be sorted into both of these two forms, and that means that most waves can kind of have a two-part classification system. What I mean by that is any given wave is, since it's either mechanical or electromagnetic, and therefore either longitudinal or transverse, you can call a wave kind of a combo name of the two. Sound, for example, is a mechanical longitudinal wave. Mechanical describes its structure, longitudinal describes its shape, the axis that it vibrates in. Sound is mechanical longitudinal, meaning that it requires a physical medium, which for humans is most of the time going to be air. If there is no air, we cannot hear the sound. And it is longitudinal in that it causes vibrations of this type. I know that because humans tend to think of waves like this, we often do visualize sound waves like this, especially in like electronic waveforms where you can, when we attempt to visualize sound, it often looks something like this, but technically the sound wave itself looks more like this. It's a small little pressure pulse of air that just travels out from the source and striking your eardrum. And it's kind of good that it physically works this way, because this is what allows an eardrum to work. Your eardrum is basically like the surface of a physical drum, just a medium that a wave can beat against. And when this pressure pulse hits that drum, since it's vibrating in the same axis as travel, it causes the surface of your eardrum, like an actual drum, to start vibrating in and out. And that is the mechanism that translates the signal into your brain. Again, like an actual physical drum beating. So we kind of need sound to be shaped this way. Bless you.
Yeah.
Earthquakes are also shaped this way, usually. And that's why the earth tends to shake back and forth rather than up and down. Either is bad, but technically earthquakes are longitudinal mechanical waves, the same as sound. I guess that means you could use sound to make earthquakes if you channeled it straight into the earth. It don't do that. I bring up that sound is mechanical longitudinal in order to point out that light is basically the complete opposite. Light is electromagnetic transverse. It's made of the opposite thing. It is shaped in the opposite way. Light is electromagnetic. It requires no medium in order to travel through, and that's why light does travel through space. You can see in space, but you can't hear in space. And it is transverse, meaning that rather than vibrating in and out in the same axis of travel, the two fields that comprise an electromagnetic wave, that being an electric field and a magnetic field, oscillate perpendicularly to travel. Ironically, it's kind of hard to visualize light. We don't see light itself. All we see is the thing that light bounced off of, if I'm being honest. But technically, if you were able to look at a photon, it would look something like this. One E field oscillating up and down, and an M field oscillating back and forth, while both travel together forwards. It's very weird. Light, again, is a very weird thing. But any type of wave you can classify with this kind of two-part system. Does a different sound all right? Pun not intended. All right. Now, since light is made of electromagnetism, which we haven't talked about yet, we're going to focus on sound for today. Because sound is just an air pulse. We've talked about air, we've talked about movement and energy, so we're going to stick with sound for the time being. As said, sound is a longitudinal mechanical wave, and the way that humans process sound, we create and hear sounds that are just pressure pulses through the air. Sound requires a physical medium, and that's why we need the air to be able to hear. Technically, you can hear underwater. Water is also a physical medium, but your eardrum's not really built for it, and that's why sound doesn't quite sound right underwater. I have not been able to have an intelligible conversation underwater, at least. As I said, the pulse of the sound wave beats on your eardrum like a literal drum, and the nerves that connect your eardrum to your brain are able to interpret that vibration in your eardrum as different sounds. And the different frequencies that you can hear, different frequencies of sound, correlate directly to what pitch you end up hearing. So if your eardrum is physically vibrating faster from a higher frequency sound wave, you hear higher frequency sound. If your eardrum is beating slower from a lower frequency wave, you hear a lower pitch sound. Questions? Okay. Human perception of sound is kind of an interesting thing. There's a certain range of frequencies that humans are able to hear. I've commented on this very briefly already. The maximum range believed of human hearing, lowest frequency humans can hear is 20 hertz sound. The highest frequency that any human has on record been able to hear is 20,000 hertz sound. I keep wanting to say that wrong. 20,000 hertz, which is very high frequency. Now, that 20 hertz, that lowest frequency, doesn't tend to go anywhere. Most humans can hear from 20 up for most of their lives. That said, 20 hertz sound is still really weird sounding. It's almost a pure bass tone, and you kind of feel it more than you hear it. I've mentioned before that when you calculate the wavelength of a very low frequency sound, they have very big wavelengths. They make a lot of air shake and pulse, and therefore when that giant column of air strikes you, you do feel it again kind of more as the pressure hitting your body more than your eardrum shaking, in my opinion. And that's why when you crank the bass, when I crank the bass, my teeth rattle more so than my eardrums. Sound below 20 hertz, you physically cannot hear. Your eardrum, it's just too slow for your eardrum to track. Like, it'll make your eardrum shake, but it's too slow for the nerves to be able to detect and process. And since it's lower than audible sound, we call it infra sound. Infra is just the root word for low. And this is dangerous to humans in high doses because you can't hear it, but it's still pouring energy into your body, and therefore it can scramble your insides if you're exposed to it for too long. Thankfully, this doesn't exist in nature in high enough doses to do that. But if you ever start feeling woozy and uncomfortable from a noise you can't hear, leave. The opposite end of this is, well, the highest frequency a human can hear is 20,000 hertz, and that is really only true the day that you're born. Because every second after that, the cells of your eardrum age, they lose their elasticity, and they stop being able to vibrate fast enough for the higher frequencies. So maybe at day one you can hear 20,000 hertz, and that decreases every single day since. I have taken a sound test, which you can, if you're following along with these slides, this link will take you to a sound frequency test where you can see what frequencies you can hear from 1 hertz all the way up to 20,000. When I take them, I tend to cap out somewhere around 16 or 17,000 hertz, which is fairly typical of someone my age, maybe a little bit low because of all the music. By the way, you can lower your max frequency early by listening to loud sounds, so be careful with headphones and concerts and construction equipment. But yeah, it does just decrease as you age, and that does mean that the older you get, the fewer things you can hear. It's not even just volume that's a problem. There are literally frequencies of sound that you just cannot process anymore when you are old. You guys, being slightly younger than me, should hopefully be able to hear somewhere between 17 to 18,000, but again, depending on factors outside of any of our control, that might be lower. Again, you can find out with this sound test. But some elderly people, if you live long enough, that max frequency might drop to about 10,000 hertz, which that's about as high as sounds that you would normally hear. Most sounds don't go above 10,000, if I'm being honest. Like 10,000 to 20,000 is rare for anything humans regularly interact with. But I have heard of some younger people taking advantage of this phenomenon by making their cell phone ringtones a super high-pitched noise that their teachers can't hear. Alternatively, some grocery store managers constantly play like an 18,000 hertz whine outside of their buildings to keep teenagers from loitering that the elderly can't hear. So, both sides have figured out how to weaponize this. But it's also a scientific reason why you might have different music taste to your grandparents. Physically, they cannot hear certain frequencies in your music. And just as a fast fact, this is the range of canine hearing, 40 to 40,000 hertz. So dog whistles are tuned between 20 and 40, and technically humans can hear dog whistles are tuned between 20,000 hertz and 40,000 hertz. They can hear more frequencies than we can, but technically humans can hear between 20 and 40 and dogs can't. So if you want to make a human whistle, put it at about 30 hertz. I think cats' hearing is comparable to dogs. Questions? All right. Speed of sound is another thing that impacts how humans process sound waves. We've mentioned when talking about wave speeds already that speed of a given type of wave is constant for that wave type and for that medium. However, if you change the properties of the medium, you change the speed of the wave. And since humans hear sound in air, that means the properties of the air affect the speed of sound. That means that factors including the wind speed, the temperature of the air, and the humidity affect the speed of sound on any given day of the week. Typically, at standard room temperatures of 25 Celsius, which is about 75 Fahrenheit, speed of sound is typically considered to be 343 meters per second, ignoring weird things like high humidity days. This drops as the air gets colder. This chart here lists the speed of sound at 0 Celsius, freezing, as 331. It's literally slower in colder air, and therefore it increases in hot air. 100 Celsius, boiling, Speed of sound increases to 386. So technically, sound hits you faster in summer than it does in winter. Now, unless you are manipulating temperature, wind speed, and humidity, speed of sound should stay constant, but it does fluctuate day to day as these things changes. I want to mention again, speed of sound does not depend on the sound's frequency nor its volume. I'll talk about how volume works later. Those don't affect sound speed. Only these three things affect sound speed. That said though, you can also make sound faster by just blasting it through a different material. Sound is about 5 times faster in water than it is in air. And that's because water is higher density. And it's even faster through solids. Earth's crust is mostly made out of aluminum, so sound is again about 3 times faster through the ground than it is through the ocean. In my opinion, that's probably why there's more echolocating creatures in the sea and underground than there are in the sky. In the sky, you really only have bats, but underwater, pretty much every aquatic mammal is capable of echolocating. It's more useful down there because the sound travels faster. You get your answer quicker. Make sense? Now, I will usually tell you what you can expect the speed of sound to be. This is a pretty common number that I will give you in any given circumstance. I just want you to understand this number changes if you change the properties of the air or if you're something like underwater. Now, we've already looked at one formula for speed of sound, or wave speed in general, that being velocity equals frequency times wavelength. But it is still just a velocity, and that technically means the old velocity formula works too. If you know the distance a wave travels in a certain amount of time, that's also wave speed. Same old formula still applies. None of our old concepts are gone. And with that in mind, let's talk about wave speed with using a slightly practical tool that you could use in your daily life. You are watching a storm, or you're witnessing a storm. You see a lightning bolt, and then 6.4 seconds after you see the bolt, you hear the thunder. You ever notice that? You see the lightning way before you hear the thunder. That is because I posted this number before, but I'll put it back up for visual effect. Speed of sound is typically considered to be 343 meters per second. Meanwhile, the speed of light is 300 million meters per second. Almost 1 million times faster. For the human experience, light is basically instantaneous. You only have to worry about the time it takes light to reach something if you're looking over very big distances like space distances. For example, it takes about 1.5 seconds for light to get from the moon to us, and about 8 minutes for light to get from the sun to us. 30 minutes to get from us to Mars. We're closer to the sun than we are to Mars. So, when it comes to viewing lightning, the light from the lightning is so fast it might as well be instantaneous. The human brain cannot process speeds this fast. So we're just going to assume that the light from the lightning occurs and hits your eye instantaneously for simplicity's sake. However, sound, being 1 million times slower, lags enough for humans to notice the difference. If it takes 6.4 seconds for the sound of the thunder to reach your ear, how far away from you was the lightning strike? answers?
$21.95.
2195. What were the units on that big? Meters, correct. It's meters because the speed of sound unit I gave you was meters per second. Meters per second times seconds, the unit would be meters. So if we wanted to use this to figure out, what am I trying to say? We can convert this to Canadian and get about 2.2 kilometers. And so this is a practical tip that you can use to figure out how far away a storm, or at minimum a lightning strike, happens from you. If you see lightning and the thunder takes 6 or so seconds to reach you, that lightning bolt was 2 kilometers away. You're probably pretty safe. If you see lightning and you hear the thunder immediately, run, get to cover. Because that implies that it happened within 300 meters of you. So, just an interesting tip in my opinion. Questions on that calculation? Related question. Would the sound's travel time increase or decrease in the heat of summer? Hot, humid day.
Decrease?
The travel time would decrease. That is correct. And that is because, tap back a second, the speed of sound increases with temperature. On a hotter day, the sound travels faster. On a humid day as well, the sound travels faster. So hot and humid will speed the sound up. The distance doesn't change, so I'm going to keep this part the same momentarily. Dagnabbit, what the heck? On the day I'm talking about sound, the light projector is getting touchy. Let's just say the speed of sound increases to 350 in the hot. Same distance, but if we calculate the new amount of time, it's going to be smaller. Not by a whole lot, something to consider. If the sound is moving faster, it takes less time to reach you. So, if you're using this tip in summer, be more careful. Because automatically that means that the sound is traveling to you faster than normal. Okay, question so far? Alright. There's one other way that you can use this basic tip, like noting the speed of sound and figuring out how long it takes to go from point A to point B. You can also use echoes to kind of clock how far something is away from you if you time how long it takes to hear an echo. Again, loads of machines and animals are capable of doing this. One thing to note, though, about echoes is they are wave reflections. Waves really like to reflect off of things. If a wave strikes something, it's pretty likely that some part of that wave is going to bounce back off of it. And when a wave does that, it travels the distance twice. If you hear an echo, how do I keep misplacing all my erasers? If you hear an echo, say for instance you scream into a cave and you eventually hear your own voice back, the sound waves you emit travel out from you, they hit the back of the cave, and then they bounce off and travel back to you, meaning that they cover the depth of the cave twice. So the same trick with the thunder and lightning you can do here. You can listen for how long it takes to hear the echo and figure out how deep the cave is. But you need to consider that the sound travels twice that distance. Either you calculate the distance with the full time and cut it in half, or you cut the time in half because it only took half that time to actually reach the back of the cave. So if you are using echoes, please note that. And technically all types of waves echo. It's not just sound. Light bounces off of things too. The only reason you can see stuff is because light bounced off of it. So, application of this. We scream into a cave and we hear our echo 4 seconds later. How many seconds does it take that sound to reach the back of the cave? Two seconds. 2 to reach the back of the cave, then another 2 to double back and cover that same distance again. So, it takes you 4 seconds to hear an echo. That is 2 seconds to actually hit whatever it bounced off of. Therefore, if you want to calculate the depth of the cave, you want to use that 2 seconds. Because that's the actual distance it covered. If you were walking in one direction, you only cover that distance once. So, you figure out how deep the cave is. V is delta x over delta t. Let's say the speed of sound is 340. It's a little cold in the cave. Calculating delta x. We're using 2 seconds, because again, that's the time to actually go one way. And this cave should be about 680 meters deep. Doesn't have to be a cave. You can also scream down into a pit and do the same thing. Anytime someone in a movie drops something into a hole and they listen for when it hits the bottom, they're using a variation of this. And again, all echolocating animals and pieces of machinery are doing the same thing. You can use light to do this. In fact, light is faster. Light will get you your data quicker. Questions about this concept? All right. While I'm talking about this concept, I just want to run a few vocab words by you. All 3 of these terms refer to using this phenomenon, using some type of wave. Sonar does this with sound, radar does this with radio, LiDAR does this with light. So, all of these words refer to this, they're just using a different type of wave to do it. Has anyone heard of LiDAR before? Technically you have LiDAR, that's all sight is.
You said sonar sound?
Yeah.
And radar is radio?
Correct.
So So they're both like audio?
Well, the thing about radio waves is they are technically a form of light, not sound. Do I have that in the slideshow? Hey, I do. I'm tabbing ahead to some notes that I'll cover later when we have time. But even though humans use radio waves to broadcast sound, the radio wave is technically an electromagnetic form of radiation, like light. Radio and light are just different frequencies of the same thing. Radio is very low frequency electromagnetic radiation. Light is mid-frequency electromagnetic radiation, and gamma is high frequency electromagnetic radiation. All of these things, radio, micro, infrared, visible light, UV, X-ray, gamma rays, they're all the same thing. They're all electromagnetic radiation. It's just a question of what frequency you're emitting or receiving. And they all behave differently based on that fact. But that means that technically your radar and LiDAR are more similar to each other than either is to sonar. Sonar is sound, using very sluggish sound speed. Radar and LiDAR are both basically forms of light, and they move at the much faster speed of light. So we use radar and LiDAR for space. Sound won't work out there. Does that answer the question? Okay. Yeah, we use radio to broadcast sound, but radio waves aren't sound waves. Just want to make that clear. All right, we're about done with sound. Just want to mention a couple more things about the human experience of sound before we close these notes. One, I want to address sound resonance. Resonance is a phenomenon that happens when you make something start vibrating at its desired resonant frequency, because all objects have a resonant frequency. It's the frequency that that object most wants to shake at. And for a lot of objects, that's just the noise they make when you hit it. If you hit something, the frequency it makes is likely its resonant frequency. That's the frequency it's naturally resonating at once it starts shaking. In fact, I forgot to grab them earlier. I grabbed some tuning forks out of the supply closet here. I don't remember which key this uses. Tuning forks are a good example of resonance because each fork is very specifically constructed to resonate at a different audible frequency. And different forks are just built differently to have different frequencies. So everything resonates at a slightly different pitch. If you hit something, it'll start creating its resonant frequency. And objects like shaking at their resonant frequency so much that if you start blasting that object with its resonant frequency, it will start shaking until it eventually shakes itself apart. That is the wine glass trick. What an opera singer, or in this case a mechanical speaker, is doing is they are just playing that resonant frequency so loudly and for so long that the object starts shaking, and the amplitude of its vibration keeps increasing until eventually it warps beyond repair and breaks. So that's how the wine glass trick works. You just have to know what the frequency of the wine glass is and then be able to hold it long enough to break it. But it's not just wine glasses and tuning forks that do this. Every object has a resonant frequency, so hypothetically, if you sing at the right pitch at anything, you can shatter it, which is what happened here. This is a rather infamous incident where a bridge shook itself apart because the wind was blowing at its resonant frequency. This bridge is the Tacoma Narrows Bridge, nicknamed Galloping Gertie, and this event took place probably, I think, around once the bridge was completed and had opened in 1940. And that same day, it shook itself apart. So this is why we care about resonant frequencies. You want to make sure that the resonant frequency of a structure is not a frequency that will ever be played near it. There's actually basically a military tactic where if an army is marching across a bridge, they will take very conscious efforts to make sure they are not all stepping in unison in order to make sure they're not accidentally making the bridge do this. Literally, it shook itself to pieces. You can look up footage if you want. This image here, that's a car on the bridge being thrown like 5 feet up, 5 feet down. So this is why we care about resonance and sound mechanics.
So you could explode a human?
Yes. Any movie or video game where a sonic attack has caused something to, or someone, to explode, technically that's not impossible. I don't know what the resonant frequency of a human skull is, and I'm glad I don't know. Questions? All right, last thing I'm going to cover, just a tiny little piece about how sound volume works. Volume does not affect sound speed. A quiet noise and a loud noise will reach you in the same amount of time. You'll just hear the loud noise more strongly, because sound volume depends on the energy that is output into the air. Whenever you make a sound, you are putting energy into the air and making the air shake. It's literally kinetic energy, you know, the energy that makes mass move because the air has mass. So volume directly translates to energy level. The more energy you put into the air, the bigger the air shakes, and therefore the more energy will hit you once that sound wave hits you. So a loud noise isn't making your eardrum shake faster, it's making your eardrum shake with bigger amplitude. As more energy pours into your eardrum, and too much energy can pop it. Frequency doesn't pop your eardrum, amplitude does. Technically, same thing here. Amplitude is what causes the wine glass to shake itself apart. And the reason that things get quieter the further you are away from them is that you put a certain amount of energy into the air when you make the wave, and that energy is now spread out over basically the surface area of a giant invisible sphere of air that is constantly increasing as the wave travels outwards. The energy level of the wave doesn't decrease, it just has to then cover a bigger area, so the energy per unit area is dropping even if the energy isn't dropping. So the further you are away from something, the less energy is in that part of the giant air bubble, therefore you get less of it, it's quieter. So that is why sound gets weaker the further from the source you are. We measure sound volume in decibels, and I just want to mention that decibels are a logarithmic scale. 10 decibels louder is 10 times louder. And 20 decibels louder is 100 times louder, because that's how logarithms work. So, for example, human conversation is currently listed here at about 60 decibels, and construction vehicles create sound at about 70 decibels. That means that construction vehicles are 10 times louder than human speech. And industrial vehicles are 100 times louder than human speech. So be careful around loud noises and industrial equipment and fireworks. Because if fireworks are 140 decibels, they're millions of times louder than talking. That's all the sound stuff I wanted to cover. At some point, I'll cover some light mechanics just because I like talking about light. But that'll be the last new material that could even possibly appear on test 2. By Friday, I will upload practice questions and the finite concept list for the test, and we'll go over that in class. Questions? All right, please have a wonderful day.